Okay, let's dive into this. Decoding AI, the mechanics of understanding prompts and context. As fellow AI engineers, you and I spend our days tuning models, benchmarking performance, and interacting with these systems. But today, we're doing a hard reset. We are looking at the exact literal mechanics of the attention pipeline. We're breaking down that foundational key, value, and query architecture that literally turns text into compute.
It is honestly incredibly tempting, even for us, to interact with a modern large language model and feel like you're talking to a human entity. You type a prompt, it parses it processes, and it replies. It feels super organic. But as engineers, we know there is no magic in the machine. There is only math. The core reality here is that the model doesn't understand syntax or human language the way we do. It maps tokens into a high-dimensional embedding space. So to get from a raw text prompt to an intelligent output, the system has to perform this highly orchestrated series of matrix multiplications. We're going to focus entirely on that translation process today, looking specifically at how raw text inputs convert directly into numerical vector representations.
You know, we so often fall into the trap of anthropomorphizing the systems we build. We tend to think in terms of lived experience, emotional comprehension, and linear narratives, but the machine, it strips all of that away entirely. It relies strictly on mathematical mapping. It chunks raw inputs into subword tokens and converts those tokens into dense vectors. So instead of feeling a narrative intuitively, the system performs rigorous data parsing. Basically, the AI is plotting your prompt on a massive invisible semantic graph to calculate exactly where conceptual clusters intersect. It's wild when you really think about it.
Tracing the prompt's exact chronological journey, we start with input generation, chopping the text string into tokens. Next up is mathematical parsing, where we convert those tokens into vectors based on the model's pre-trained weights. Now, what's really interesting about this slide is step 3, establishing context, because having embeddings for isolated words just isn't enough to generate a coherent response. Think about real-world token mapping in code, for example. The word return means something totally different inside a Python function definition compared to a standard English paragraph, right? Quantifying that precise relationship and establishing the dependency between those tokens, that is the most computationally heavy and mathematically complex part of the entire pipeline.
Moving on to Section 1, Deconstructing Context, Key, Value, and Query Terms. Let's pull back the curtain on this black box and look directly at the exact key, value, and query vectors driving the attention mechanism. Starting off with the query, or Q. Think of the query like a specific search criteria in a database, broadcasted by the current token being processed. As an attention head processes your input, it generates a query vector that represents exactly what this active word needs from the surrounding context to resolve its own meaning. So, for instance, if the active token is a pronoun, its query vector is mathematically seeking out a preceding noun to resolve its reference. The query is basically the active token scanning its environment, searching for semantic relationships to anchor itself. Now, if the query is the search, the key, or K, is the broadcast label or advertisement. Every single token in the sequence generates a key vector advertising the exact type of semantic information it holds. So when the query vector from our active pronoun goes searching, it computes a dot product against the keys of all the preceding words in the sequence. This is a direct mathematical comparison. And when those vectors align mathematically, meaning the query's search criteria matches the key's advertised semantic payload, we get a high attention score. That high score signifies a crucial contextual match between those two tokens.
Okay, so once that high attention score is calculated, the value, or V, comes into play. The value is the underlying payload of meaning, the actual contextual data being transferred when a query successfully aligns with a key. We take the value vector of the matched word, scale it by that attention score, and synthesize it. This contextual data is essentially transferred over, updating the model's internal representation of the current token. And this mechanism is exactly how the system tracks long, complex conversations within the context window. It's just constantly pulling values from previous tokens to enrich the meaning of the active token being generated.
And this brilliantly illustrates what context actually is to an AI system. Bringing these three components together, seeking with the query, matching with the key, and extracting meaning with the value, shows that context isn't a persistent memory state or human comprehension. It is literally the continuous matrix multiplication of queries mapping to keys and pulling values, thousands of times over. This KVQ pipeline runs continuously across every single token, weaving isolated data points into an interconnected semantic web. By continuously calculating these dot products, the attention mechanism dynamically updates its understanding of the entire prompt token by token.
To summarize our core engineering takeaways for this explainer, AI understanding is fundamentally a mathematical mapping of dense vectors. Prompts rely entirely on this KVQ architecture to process and generate context, and ultimately what feels like an AI's memory during a session is just this continuous synthesis of queries, keys, and values in action, stored temporarily in the model's KV cache. Keeping this mechanical reality in mind really strips away the illusion of intelligence and allows us to see the exact data processing pipeline that makes these models functional.
But as we all know, this elegant architecture brings a massive engineering bottleneck. As a prompt grows, calculating Q, K, and V against every single previous token causes the KV cache to absolutely explode in size. This is why we hit hard GPU memory limits. It's the exact reason we constantly troubleshoot CUDA out-of-memory crashes in production when context windows are pushed too far. I'm sure many of us have sat there and watched a large language model crash during a massive document ingestion purely due to this vector memory overhead. So as we benchmark performance and try to scale to millions of tokens to ingest entire code bases, standard attention simply doesn't scale. How will the KVQ architecture handle infinite context? Will we rely heavily on optimizations like flash attention, or pivot entirely to alternative architectures like ring attention or sparse attention to reduce that overall memory overhead? Solving the KV cache bottleneck isn't just a minor optimization problem. It is absolutely the next great frontier in AI engineering. Thanks for joining me for this explainer, and I'll catch you in the next one.